Hello ladies and gents, I hope your studies are going well. Maybe this little video will assist in some conceptual and a few calculational ideas. The topic, as you can see, factors affecting solubility. So what is it that allows one solute to dissolve in another solvent? Well, you know one of them. If you've watched a previous video, we've talked about like dissolves like. Water, being polar, dissolves other polar and ionic substances, or many ionic substances, and many other polar substances, but not nonpolar substances like oils and waxes and molecules that are perhaps too large without too much polarity overall. Here's another clue to another factor. What if I had two solutes, actually the same solute, differently, they look different. This is sucrose, and this is also sucrose. But which one do you suppose would dissolve in the water faster? Or, if you ask yourself, if someone gave you a big chunk of salt, like a salt lick used for a herd of cattle or something, how could you dissolve that in a big swimming pool of water faster? Well, isn't the answer obvious? Don't you have to grind it up into small particles, and that would definitely help get more surface area of the solute in contact with the solvent, and in a sense the solvent particles collide with the solute particles more quickly or more frequently, and therefore the dissolution, the dissolving happens a lot faster. Well, duh. Stir it, shake it, agitate it, get it going. You don't just pour the salt or the sugar into the water, let it sit there. If you don't want to heat it up, then another option is to stir it and shake it and grind it up into small particles. Oh, I was a bad teacher. I just said it a second ago. Heat it up. I got to warm it to a warmer temperature. Here's a graph similar to one you might find in your book. The bottom axis is temperature, and the vertical axis, the y-axis, is solubility. And let's see, if I look at, I wonder if I could shrink this down a little bit so you could see the axes at the same time. There we go. If I look at any one particular solute, the solvent is water, solubility in grams of, it says grams of salt in 100 grams of water. So for some reason, almost always the solubility of particular compounds is described in grams per 100 grams of water. So if I just pick lead nitrate or something, pick the yellow line, I know that 50 grams of lead nitrate would dissolve in 100 grams of water if that water was at least 15 degrees Celsius. That's pretty cold. Or anything warmer is certainly warm enough. Any water that's warmer than 15 degrees would also be able to dissolve the 50 grams of lead nitrate. But if my water temperature were only 10 degrees or 5 degrees or 1 degree or 0 degree water, that water would not be warm enough to dissolve the entire 50 grams of lead nitrate. Or if I wanted to dissolve more lead nitrate, let's see if I have one here that's a nice even, I don't really have another one. What if I wanted to dissolve 70 grams of lead nitrate in 100 milliliters of water? I follow the axis down and find the water would need to be at least about 34, 35 degrees Celsius. Let's pick on another chemical. Let's pick on this potassium dichromate. Nice sloping line right here. Question, would 70 grams of potassium nitrate dissolve in 100 grams of water that is 60 degrees Celsius? The answer is no, it wouldn't. That's not warm enough. If I wanted 70 grams of KNO3 to dissolve in 100 milliliters of water, my temperature would have to be 90, 91, 92, or somewhere very hot up in here. So anything in this region up and left of the particular chemical you're looking at, the water's not hot enough, or you could also say there's too much chemical for that particular temperature of 100 grams of water. Let's see. So if I stay with potassium dichromate, and I ask the question, would 40 grams of potassium dichromate, would 40 grams of that dissolve in say 70-degree water? And the answer is yes, 70 degrees is warm enough to dissolve 40 grams of that K2Cr2O7, potassium dichromate. So anything below the line, or to the right of the line is warm enough to dissolve all that solution. Or if I said I had 30 grams of potassium dichromate dissolved in 50 degrees Celsius water, I know that solution would be saturated. It would be a perfect balance of holding as much of that solid solute as it possibly could. So the answer is temperature. For most solid solutes, warm water will dissolve more solution than cool water. And I summarized what I just did here. For any one particular solid solute solubility curve, if you're on the curve, you're exactly saturated. The water's holding just the right amount of chemical. Nothing more could be held. Something less could be held. But if I was above and or to the left of the curve, I describe excess solute, and my solvent can't dissolve anymore, and some remains sitting on the bottom of the beaker. Or if I am below the line, my temperature is warm enough, and I would be unsaturated. I could certainly dissolve a little bit more. There's another case called supersaturation, where you actually warm up the solution and hold more solute than it normally would. You warm it up on a stove, and then you let it cool off. And sometimes if the solute is just particular to that solvent, then that solution might be able to hold more solute than it normally would hold at that temperature. And it becomes what we call supersaturated. I'll show you a demonstration with that during a lecture. What about gases? Nitrogen monoxide, oxygen gas. Let me shrink this down a little bit more so you can see more of it. All at the same time. Let's see. Nitrogen gas, methane gas. Looks like their solubility goes down as the temperature gets warmer. So 2 grams, 3 grams, 4 grams, 7 grams, 10 grams of, that's milligrams. My goodness, that's a small amount of gas in this temperature of water, 100 milliliters again. Why would the solubility of gases decrease as the water gets warmer? And we got to think about this on a teeny tiny scale. The answer is what we think has happening in terms of a molecular or subatomic model is the water particles are moving so fast they collide with the gas particles that are somehow surrounded or solvated by the water. And if the water pushes into them, bounces off them so quickly, it kind of pushes them out of solution. So this is a problem for fish and aquatic life that depend on dissolved oxygen in the water. If the water gets too warm, the dissolved oxygen goes down, decreases, and the poor little fishies basically suffocate because they can't get enough oxygen from the thermally polluted water. There's also pressure. Pressure makes a big difference if you're talking about a gas. So here's a gas dissolved in water with also some gas in the gaseous phase, aqueous phase, gaseous phase, that same molecule above the water. And in some kind of equilibrium. There's some of the gas making it escaping up into the airspace and some coming from the airspace dissolving back into the aqueous phase. It's a nice balanced mixture. But if I brought this plunger up higher so that there's more space for that gas to roam around, I don't know if you can imagine, but more gas will escape from the liquid, making it up into the airspace, and less gas will be dissolved in the water. And the opposite is also true. If I push the plunger down this way and increase the pressure, partial pressure, total pressure of this gas above the aqueous phase, then more of those molecules will be forced down into the liquid phase, into the aqueous phase. And in a sense, gases are more soluble if the pressure upon them, upon that solution, is greater. It's called Henry's Law. Henry's Law states something like the concentration of a concentration or solubility of a gas in a particular solvent depends on this constant K that's exactly specific to the gas and the pressure and atmospheres above it. This could be in moles per liter, molarity. This could be in atmospheres. So my gas constant, my Henry's law constant, would be in atmospheres per molarity. Here's a few examples. Specific to that gas in question: carbon dioxide, oxygen. Here's a mathematical calculational question. What's the solubility of argon gas into an aqueous solution considering a pressure of argon above the solvent solution, pressure of argon 50 atmospheres? Well, let's see here. I know that my constant for argon is 50 atmospheres, so all I really have to do is multiply those two. 50 times 0.14, that's the constant that was given to me, 0.07 moles per liter of argon. So if I had a liter of solution, I could fit only 0.07 moles of argon into that with that particular pressure. And I'm thinking this is temperature dependent as well. Temperature dependent? Yeah, it must be. Because, of course, warmer liquid could not hold as much. Here's one more for thought. Work on this one if you feel like it. Want some practice? What's the concentration of gas X in a saturated solution at 25 Celsius and 64.2 atmospheres of pressure? Oh, they tell me the concentration, the solubility. Some books use a capital S for this C here. They put a capital S for solubility, how much will dissolve. What's the concentration? Oh, the concentration is 0.0035 molar. And it wants to know this constant of proportionality. Hey, thanks for listening, guys. See you in class.